today we'll talk about linked lists. But before we start to talk about linked lists, I want to introduce another computational model. As you may remember from the first lecture, we were talking about computational models, and we decided we'll almost always use the RAM model. So in all previous data structures, we use RAM model. RAM model, let's remind you. So it's the model when you have a RAM, like a big array of data, and you can access any element of this data by index. Cool. And now we will switch to another computational model. It's called pointer machine model. So what is a pointer machine? Pointer machine is a very simple computational model. In pointer machine, all your data is stored in some nodes. So you may have like big number of nodes. Each node, let's say node X, may have some constant number of fields. Each field contains some data, like objects in Java. You may have some fields. Each field contains some data, like name or something. Let's see, like I need to get the name of the fields. Let's say I have field A equal to 5, B equal to 7, and so on. So just some data stored in this node. And you may have some fields which points to another node. Let's say we have field P, which points to node Y. So we have another node Y. So this field is a pointer to this node Y. And you may have pointers to any node. You may have pointer to itself. You may have pointer which points nowhere, just to null, something like that. It's mostly like you have classes in most programming languages, like classes in Java, classes in Python, something like that. That's all you have in the pointer machine model. What operations can you make? No, you may make like very primitive operations like create node, like X, new node. You may remove the node, like if you need some memory, and you may change the field of the node, let's say X dot B equal to 10, or you may change it to pointer nodes, like you may change this pointer field to point to another node, let's expect Z. So you have another node here, so you may change this pointer to here, and so on. No, I will not upload. Yeah, home task discussion is not uploaded to YouTube for reasons. So it's only available on Twitch, and there are reasons for it. Cool. That's all. Now, what is the difference? What is the main difference between pointer machine model and RAM model? The main difference is that in pointer machine model you don't have arrays. So, in RAM model you obviously have arrays. You may create an array and access any element of the array by its index. Yep. Well, obviously, in RAM model, you can access any element by index. So you can create a segment of this RAM, call it an array, and access any element. In pointer machine model, you don't have any arrays. You have only these nodes, and each node have a constant number of pointers. So you can have pointers to each element of the array. because a constant number of these pointers. So in point machine models, you need to create some data structures which doesn't use any arrays. That's all. Yeah, I think that's all. It's a little bit strange. Why do you need to use pointer machine model when you can use RAM model, and you may have the arrays in RAM model? So why should you use pointer machine model instead? We will talk about later. So sometimes it's good to have pointer machine model instead of some more powerful model like RAM model. So we will talk about later. Now we'll go to linked list. So in pointer machine model, you don't have arrays, but you usually want to maintain the lists of elements. So how you create lists of elements when you don't have arrays? And the linked lists work like that. So you have a number of nodes. Each node contains one element of the list. And you have pointers to the next element of the list. So in each node you have one special field. Let's call it next, which is the pointer to the next node of the list. So from here you have a pointer to this element. Here you have another next to this element. Here you have another next. And also in each node you have some important data, like here you have some data. Data is the data you use in your algorithm. And in addition to this data, you have this special field, which is used to create this linked list. And also you need, I think you need the pointer to the first element, like the pointer to here, like first. And from here, next points to null. Yeah. Good. That's all. That's how you create a linked list in pointer machine model. So how to use this list? What can we do with this linked list? For example, we can iterate over all elements. Like what you do when you have arrays? You do something like that. Like for I from 0 to n minus 1, print element like this. So that's what happens when you need to iterate over all elements of the array. Here we don't have the array. We have this linked list. So how to iterate over all elements of the linked list? We just go from the first element, and on each step of this cycle, we go to the next element of the list. So let's say we have current element equal to first. And now we just jump to the next list, to the next element of the list. So while then x not equal to null, we just print element x and then jump to the next element. Something like that. That's all. That's how you iterate over all elements of the linked list. Now, what else can you do? What else can you do? You can do in the linked list comparing to arrays. Obviously, what you can't do in linked list, but you can do in arrays, is access the element by the index. So if you want to find like the element of index I, you need to go from the first element and use these pointers until you reach the element of index I. So to access this element, you need to start from the first element and get to this element from left. So you may need up to n time to find this element in the linked list. And in the array, you can access any element of the array in constant type just by using this indexation. Okay? But what can you do in linked list but you cannot do in arrays? No, one obvious thing you can do in the linked list is to insert a new element in the linked list. For example, if you want to insert new element between two existing elements of the list, like you have these two elements, let's say we have element X and element Y, and we want to insert new element here. So we want this new element, let's call Z, and you want to insert this element Z between these two elements. When you have arrays, you cannot do it fast, because if you have arrays and you insert new element in the middle of the array, you need to like shift all the elements to the right. And here you can insert element in constant time, because all you need to do is to move this link to here, this link to here, and remove this. And you're done. Let's write it. Let's have procedure like add after X, Z. So we need to add element Z after element X. Let's say Y equal to X next. Then we need to put X next to Z and Z next Y, right? That's all. That's how you add a new element to the linked list. And you can add element to any position of the linked list. The only difficulty is that if you want to add Z into some position on the linked list, you need to have pointer to this element X. So you need to have, from somewhere, you need to have pointer to this element X. And if you have this pointer, you can add new element after this position. Okay. Oh. Okay, this studio is not that stable. Huh? Fine. Next, how to remove elements from the linked list. If you need to remove the element, let's try it here. You need to move the pointer from the previous element to the next element. So you need to move this pointer to here. And to do this, you need to know the previous element in the linked list. So if you want to remove this element X, you need to find the previous element in the linked list. So if you know the pointer to the previous element, then it's fine. You can just get the pointer to the previous element and move this next pointer to this element, to element after X. But if you don't have the pointer to the previous element, that's complicated. So you cannot just, in this realization of linked list, you cannot remove element just by having the pointer to this element, because you also need to have pointer to the previous element. Yeah? This pointer like hard-coded index. I don't get it. What is hard-coded index? Not sure about what you're talking. There's no like indices here, so it's more like, well, like there are some entities you have like pointer. Pointer is something which allows you to get information about this node. It's hard to know how it is realized in the real system. It may be complicated. So in the real computer, it may be implemented in various ways. So usually you have like. Usually in real computer, let's go back. Usually in real computer you have something like RAM model. Usually, so you have in most computers you have some RAM, and you have something like RAM model. So when you try to implement something in pointer machine model, you need to somehow simulate this pointer machine model. So you have some elements, they are stored in memory, and you have these linked. These links are kind of indices in RAM, but you may implemented in various different ways. So you may move these objects, so you move these links, and just at least as long as if you maintain this structure somehow, you're good. And there are various ways to maintain this structure that have different good properties. I'm talking too much. Let's go back. We will talk about later. Yes, a little bit later we'll talk about why you may want to use pointer machine model instead of RAM model. What I was talking about? Removing. So, if you want to remove the element, you need to point to the previous element. So usually, if you need to have a list which can be used to remove, and you want to be able to remove elements from this list, you use not list like that, but you use double linked list. What is double linked list? It's the same linked list, but you have pointers to previous element, to next element, and to the previous element. So in each node of the linked list, you have two pointers. One pointer to the next element and another pointer to the previous element. So this pointer is a pointer to the previous element in the linked list. This is null. Cool? Fine. So let's modify this procedure first. So if we want to add a new element in the double linked list, so we have new element Z. So we need to have pointer from here to here, from here to here, from here to here, from here to here. So we need to modify these four pointers. X next to Z, Z next to Y, and also Y pref to Z and Z pref to X. And here already I made my first mistakes because here, no, not here, that is Y, here you may have a null pointer exception. Why you may have null pointer exception here? Because if you add a new element after the last element of the array, so if this X is the last element of the list, then Y is null. So here you try to access the element of the null pointer, and you have a null pointer exception here. So to avoid this, you may just write something like, let's say, if Y is not null, then Y pref equal to Z. And Z is not null, X is not null, so it's fine. Something like that. How to remove elements? So let's remove some elements. So we have this element X, we want to remove it. Let's have previous, next, previous, next. Let's call this element Y, this element Z. So if we want to remove element X, let's find the previous and the next element. And move this pointers. We need to move Y next to Z and Z pref to Y, like this. But both of these elements may be null. So let's say if Z is not null, this, use the same notation. So if Z is not null, then we put pointer pref to Y. if y is not null, then we move next pointer to z. And also, if y is null, it means that we need to move the first pointer. So we also have this pointer first to the first element of the array. And if we remove the first element of the array, let's say if x is equal to first, then we need to move first to the next element, z. Why is that correct? So I have this element x, the previous element is y, the next element is z. Here. So here, this element is y, this is z. So z prep to y, y next to z. No, it looks fine. That's all. So this is how you remove the element from the double linked list. And as you may see, we already have, even for these simple functions, we have many if statements. So we have too many if statements. We have if here, and if here. And when you have too many if statements in your program, it's not a good thing. Because if you have too many if statements, you need to test all of them. Yes. And if some of these if the statements doesn't work, you may have some bugs in later. So it's usually better to have program which have not so many if statements. So how can we do it here? One of the tricks that you make when you have a linked list is to add two special elements in the beginning and in the end of the linked list. So what you may do is to have two additional elements. You have these elements of your linked lists, something like that, and you add two additional elements. Additional element here, and another additional element here. And you put link first to this element, and last to this element. That's all. And now you have something like a deck, basically. So you can access both the ends of this linked list. You can add some elements here. You can add some elements here. You can iterate all elements in either direction. So you can go from left to right. You can go from right to left. You can add anything, remove anything, and you don't have these if statements because you don't remove these both end elements. You can only remove elements in the middle, and for each element here, you have the pointer to the previous and next element. You always have these two elements, so you don't need to check if you have null pointers there. That's how it works. And also you don't have this if statement because this y cannot be null. That's all. You can even have more simple this structure. Let's see. So in this first element, we only use this next pointer. And in this last element, we only use this previous pointer. So instead of having these two additional elements, we may have only one additional element. So we may add one extra element here. And from this extra element, we put the next pointer here and the previous pointer here. So we have some like cyclic lists. Yeah. And this is actually one of the most common ways to use the linked list. So again, how to use linked list? You have this, each list is identified by this element. So if you want to have like a pointer to the list, you have the pointer to this element. So this is the pointer to the list from somewhere here. So if you want to access this list, you use this pointer, go here, and then you can do anything. So you can iterate from left to right, you can iterate from right to left, you can go somewhere and add some additional element and so on. That's all. Nice. What else can you do with linked lists? For example, you can concatenate two linked lists. So if you have two structures like this, let's have another structure here. If you have another structure like this, so you have another element like this, and you have some list here. Something like this. There are double links everywhere. So you have list link to this element, and you want to concatenate these lists. So what you can do is basically remove one of these additional elements, put link from here to here, from here to here, from here to here, and so on. So instead of two lists, you have only one list, big list. So you can concatenate two lists in constant number of operations. And now various stuff like this. You can split lists into two parts, you can concatenate two lists, and so on. Cool. Fine. Now, let's go back to stacks and queues. So on previous lecture, we discussed what is a stack, what is a queue. There's two important data structure, and they both can be implemented in pointer machine model in a very simple way. So if you have, for example, stack. So in the last lecture, we used array. We use arrays to maintain the elements of the stack. And now instead of arrays, we will just use the linked list. So how to implement stack when you only have linked list? Well, let's see. So we have the elements of the stack. So let's say this is the last added element, so this is the top element of the stack. You may have a double-ended list like here, but actually you don't need this. It's enough to have a single direction linked list. So in what directions do we need pointers in this linked list to be able to maintain the stack? It looks like, how to think about this? So let's think in what direction we need links, from left to right or from right to left. When we need to link to another element of the list, when we need to go from one element to another, when we remove this top, so when we make a pop operation in our stack, we need to move this top pointer to the next element to the left. So we somehow need to be able to jump from here to here when we make pop operation in the stack. So we need to have pointers from right to left, like this. And that's actually all we need. We will never use the pointers from left to right. So we will maintain the single direction linked list, and we will maintain pointers from right to left here. Well, let's implement both operations of the stack. We have only two operations. Let's implement them both. So when we need to push, So I want to push new element in the stack. So we create new element here. Make this pointer from here to here and change top to here. That's all. That's how you push element in the stack. What's that? Just x next to top and top equal to x. Yeah, basically all. That's how you push element in the stack. And how you pop elements from the stack. Well, like before, we have the pointer to the top element of the stack. We need to move this pointer to the next element in the list and then return this element. So it's, just remember the previous top, move top to the next element, and then return this res. That's all, very simple. It's not surprising that it's simple, because it was simple even when we had arrays. So it's surprising fact that it's not much more complicated in pointer machine model than it was in RAM model. But it was very simple in RAM model. Like we had one line for functions push and pop, and here we have almost the same. So we have some small number of operations for each operation. That's all. That's how you make stacks using linked list. And queues. How do you create queues in the pointer machine model? Well, it's almost the same. So we have some number of elements. We have the pointer to the head element of the queue and to the tail element of the queue. And we need... In what direction do we need to have pointers? Well, let's think about it. So when we add new element to the queue, we just add element here and we need to move from this element to this element. So we don't need any pointers, we just move tail to this new added element. And when we remove element from the queue, we remove this element head, and we need to move head to this next element in the queue. So we need to somehow to jump from here to here. So to be able to do this, we need to have pointers to the next element of the queue. So we need to have pointers like this, from left to right. Yeah? 35 minutes? What 35 minutes? Since we started? Yeah, it's about 35 minutes. That's pretty quick actually. Yeah. Okay. Okay, let's do it. So what happens when we add new element? Little bit more complicated when you may have empty queue. What happens when you have an empty queue? There are two ways of doing this. You may have both pointers equal to null when you have an empty queue. Or you may have additional element here. And like when queue is empty, you just put all the pointers to this additional element. Let's do it in a hard way. Let's say that if queue is empty, then both these pointers are pointed to the null. Let's go. So how to add new element? So we just add new element here. And here, if the queue is empty, now always we'll need to have these ifs. So if queue is empty, then we just create new element x and make a queue of the single element. Yeah. Yeah, good enough. I have these new projectors too for lighting, but yeah, it's kind of strange. What I was talking about? When you add new element, if the queue is empty, then we add new element and make a queue of the single element. And now, if the queue is not empty, then we just add new element here, move this link and add this link here. So we say from tail equal to x, tail next to x, and tail equal to x. Looks fine. That's how you add new element to the queue. How you remove element from the queue? Which country comes from? From Russia, supposedly. I'm from ITMO. Please don't ask questions in Russian. You will just block me. I cannot understand Russian and English in the same time. Just I switched to Russian for a moment and now I need to go back. Fine. So how to remove element from the queue? So again, you take this element head, remove this element, and then move to the next element here. Yeah. Again, let's remember the position of the head. Now we need to move head here, and we need to check if the cube became empty. Yes. So if queue contains only one element, so if head equal to tail, then we remove this element and make an empty heap. And if not, then we just move head to the next element. Looks fine. Is it correct? Looks correct to me. That's all. That's how you implement the stacks and queues in the pointer machine model. It's pretty simple. You just have a single linked list and you make the procedures like that. Looks fine. Looks fine. Okay, let's go to the next topic. So, why you may want to use pointer machine model instead of standard RAM model? Because you may want. The trick is that sometimes when you have more simple computational model, it's easier to analyze it because it's simple. You have simple operations. You always have this. It's structured, so you have only these pointers. So it's easier to check what parts of your data structure may be changed by your algorithm. For example, in RAM model, you have some segment of your memory, and you may have someone else here to access your memory just by index. So if someone have index in your array, he may just change the elements here by just by having the index of this element. In RAM model, it cannot happen. You only can change the fields of the node by having the pointer to this node. So to be able to change the element here, you must have the pointer to this node. So it's easier to check what other elements have access to your node. So if you have some nodes, you may just have the list of all pointers to your node and always know which nodes can have access to your node, something like that. Why it may be important? Because you may want to make something like garbage collection, for example. How the garbage collection works in Java, let's say. You have some classes, each have some objects, and these objects have links to another objects. It's mostly like it's done in pointer machine model. It's a little bit more complicated in pointer machine model. You may have arrays in Java, obviously, but the idea is pretty much the same. So if you have something like you have some objects and you have links to this from one object to another, and so on. And if at some point you find that, for example, you change this link to here, so you remove this link. If at some point you find out that this object cannot be accessed from another object, you may understand that this object is not accessible, so it can be safely removed. So you just erase this object from the memory, and it's safe because no other object can access the elements of this object. So you just remove this object, and all objects depend from this. If you have any other objects here, then garbage collector will also remove all these objects as well. And you can do it automatically. You cannot check it manually. In Java garbage collector, you will just find out this situation and automatically remove these objects from the memory. That's how it's working. Another example is, for example, parallelism. When you want your data structure to work for several threads in parallel, so if you want some concurrent data structures, then it's much more easier to have very simple computational model. Because if you have computational model like this, like pointer machine model, again, if you have several threads which concurrently operates on the same data structure, then you want to be sure that if you change something, no other thread can access this element. And what you can do in pointer machine model is just to maintain the set of all nodes which have a pointer to your node. So you always know which other nodes can access your node. So all parallel operation become much easier. So there are a lot of different strategies how to maintain parallel operations in pointer machine model. And the final thing that we will discuss today, I will not talk about parallel data structures, and I will not talk about garbage collection. But what I want to talk about today is how to make a persistent data structures in pointer machine model. What is persistent data structures? What can I raise? Let's raise this. Persistent. So what happens usually when you have data structure? you have some data structure. Let's have, so this is data structure. Some data structure. You make some operation on this data structure, like add new element, remove some element, change some element, and so on. So you make some operation which changes the state of the data structure. Operation. And data structure moves to another state. So this is the state of the data structure before the operation, and this is the state of data structure after the operation. So what usually happens? Usually happens that you only have this right version of the operation. So you make the operation, so you change something, and you forget what happened before. So you forget this state, and you only have this state of the data structure. In persistent data structures, you want to maintain all the history. So you want to maintain all the previous states of the data structure. That's so. You may have access to this version and also to this version of data structure. That's the idea. Why you may want to access the previous version of data structures? There are reasons for this. For some algorithms, it's good to have states of data structure. For different reasons. Like you have graph and you add edges one by one, and you want to access the graph which was before we added these nodes, and we want to have access to another graph which have all these nodes and so on. So in some algorithms it's good to have some persistent version of data structures. Not clear enough, right? No. But I believe we will talk about persistent trees in next semester, not today. Let's talk about, yes, sometimes it's important, sometimes it's good to have access to all previous versions of the. Yes, you may think about like a version control system like Git or something like that. Yeah. Is it Git or Git? I think it's Git. Not sure. That's all. That's what we will try to do. That's what we will try to do now. Interesting result that almost every data structure which is built in pointer machine model can be made persistent without any additional asymptotic cost. So that's almost true. Almost any data structure built in pointer machine model can be automatically transformed to another data structure which does the same operations, but it is persistent. We will not talk about this universal process, but we will talk about some data structures and how to transform these data structures to persistent data structures. For example, let's have a persistent stack. So we have this stack. And we want to make it a persistent one. So for example, now we have some state of the stack, like this. Let's have some. So we have this version of the stack. Let's have it, let's say it's version 1. Like this. And now we make some operation to the stack. For example, we push some new element to the stack. Let's put some values here. Let's have some values like A, B, C, D. Yeah. And let's push something. So let's push E. Push some element E to the stack. So how do you push elements in the pointer machine model stack? So just create element E here. And make pointer here. And now you move the top pointer to this new element. And if you want to maintain both versions of the stack, this version 2, you just maintain these 2 pointers to the top. Well, so you maintain 2 pointers to the top elements of the stack. So this will be the pointer to the top element of the version 1 stack. It's the top one. And this will be the pointer to the top element of the version 2 stacks. And now on this picture we have both versions of the stack at the same time. So if we start from the element D, you will get the stack before we push this new element E. And if you start from here, then you have the stack after we add element E. So you have these two stacks simultaneously. So this stack can be accessed by accessing this top element of 1, and this stack can be accessed by this element top 2. That's all. Let's have some more operations. So you start from this version 2 and then pop this element. So what happens when you pop element from this stack? Well, you simply move this top pointer to the next element in the list. So you want to move this top pointer back to this element D. And let's have version 3 here. So in version 3, we have the same stack, but the pointer to top element points here. Okay. Yes, you need to do it starting from the first version. So you start from the empty stack, and on each iteration you add new element and maintain this version. No, you only need to maintain the top elements of the versions you will need in the future. So if you need all versions in the future, then you may need some lists of these top elements, something like that. If you need only some of these versions, then you may have some pointers to the version. For example, if you know that in the future you will need access to this version 2 of the stack. So you just save the pointer to this element top 2 for future. And then in the future, when you need to access this version, you go back. How to access version 2? Now again, we have this 3 versions. We have version 1, version 2, and version 3. Now, if we want to access version 2, we take this pointer, which points to this element E. We have pointer for version 2. This is the top elements of the version 2 stack. And let's have a branch here. So if we branch from these elements, for example, so I want to move back to the version 2 and then, for example, push another element. And have version 4 here. Then what will happen? I have this element E. I add another element F here. Make link here and make top 4 to this element. Now I have 4 different versions of this stack. And let's make it interesting. Let's push some element here. So if I push from version 3 some element G to version 5, then I need to take the head element, top element of the version 3. It is D. Then add element G. More markers. And connect it to the top elements of the version 3. So I have version 3 ended here. So I have connection here. And have top 5 points to this element. That's all. So you have something like tree here. So it's like tree of elements which was added to different top elements of different versions of this stack. But this tree contains all the states of the stack. So if you want to take, for example, stack 3, you take this stack, find the top element of the stack 3. So from here you have the state of the stack 3. And from here you have state of the stack 5, and so on. So for any version, so again, you need to have the pointer to the correct to your version. You don't have arrays in the pointer machine model, so you somehow need to have pointer to the version you want to use. That's all. That's all. That's how it works. That's the persistent stack. Persistent stack is one of the simplest persistent data structure, actually. Some data structures are much more complicated, but persistent stack is quite simple. Let's move to the queue. Can we do the same with the queue? Can we just use the same technique and apply it to the queue? It looks like it's not a big difference, but it actually is. What is the big difference between stack and the queue? We have head here, we have tail here. What is the difference? So imagine you have this version. Again, this is version 1. And then you add another element to the queue. So you move it here. This will be tail 2. So tail 2 will be here and head 2 will be here. Let's try to use the same technique. Like, remember these pointers to the elements we need to use when we move to the next version. So for each version, we will have 2 pointers, the head element to the tail element. That's what we need to maintain the queue, right? So for each version, let's remember these 2 pointers, the head element to the tail element. Again, when we add, here we add another element to the queue. So we have head points here, tail points here. What will be the problem? The problem will be when you will try to add another element to the version 1. So if you want to take this version 1 and add another element instead of this. So if you want to branch here and add another element. Then what you need is to have another element here and make a pointer here. But you can't do it because you already have pointer to this element. You're not able to have 2 next elements for this tail element. Yes, you only have 1 pointer to the next element, obviously. So you can do it. That's the problem. There are various ways to solve this problem. Let's just see it. Do we have enough time to talk about this? Not sure about this. One of the simplest way to solve this is to build a queue on top of the stacks. Last lecture we discussed how to build queue from 2 stacks, right? Just last lecture. So you may remember that. What you can do, you can make a persistent stack. So you can take 2 persistent stacks, and make a queue out of them. That's one of the obvious ways to solve this problem. Like okay, I know how to make persistent stack. So let's take 2 persistent stacks and make a queue. And that's almost true, but not exactly. What is the problem? Why can you just take 2 persistent stacks and make a queue? You can, but it will be slow. Why is it slow? Because the stack, when you create a queue out of 2 stacks, it has constant time of all operation, but it's constant amortized time. So if you so if you make queue out of 2 stacks, you will have queue with constant time of all operations, but it's constant amortized time. Yeah, like you can watch the previous lecture on YouTube. It was pretty nice. So you'll have, and here you have constant amortized time. And when you have the amortized time of the operation small, you cannot just create a persistent data structure. Because what will happen? So you have some versions of your data structure. And the amortized time is small. What does mean the amortized time is small? It means that if you have some long operation, then the potential function of your data structure is decreasing. Like, yeah? Yeah, we discussed it last time, just a week ago. I believe you remember this. Imagine you have some long operation here. So this operation is very long, but it decreases the potential function. So you have potential function is big here, but it is decreasing here. So this long time is compensated by decreasing of this potential function. So the total time, amortized time, is small. Do you remember this? Okay, I believe you remember this from last time. So what will happen when you have the persistent data structure? You may want to make this long operation and then go back and make another long operation. So you may go back to this version and make another long operation. And the potential function here is also small, so this operation is also long. And you can do it many times. So you can go here, then go back, then make another long operation, go back, then make another long operation, go back, and so on. So all operations are long. So the amortized time will not be small. That's what happened. So that's what will happen if you try to make persistent data structure from the amortized data structure. And yeah, the way of solving this is by using not amortized data structure. You can make a queue out of stacks with constant time, not with real constant time. Not today, I think, but you can read about this. You can make queue out of stacks with real constant time of all operations. It's a little bit more complicated than amortized time. So you need you need to have one input stack, one output stack, and when this stack is empty, you need to transfer all elements from this stack to this stack. But you can transfer not all at the same time, but one by one. So on each operation, you transfer some elements to the new stack. But there are some difficulties. You cannot transfer elements because you will add more elements. So you need to have some buffer stacks, and so you transfer them to these buffer stacks, then transfer them to the next stack, and so on. So you may build the non-amortized queue from like 5 stacks. I know how to make from 6 stacks. I believe it can be made from some like 4 stacks. So it's possible, but not today. What I want to talk about is a little bit different thing. Sometimes you don't actually need things like this. Sometimes you need to have persistent data structure with some linear order of the versions. So you only make these operations in linear order. So you only modify the last version. Sometimes it's happened. So sometimes in your algorithm you need persistent data structure, but you know that you will never go back and modify this version. So you don't have situations like this. You have some linear order of your operations. It's kind of strange for the queue because in queue all operations modify the queue. But if you have some data structure which have operations which don't modify the data structure, like some queries, like how many elements we have, and what is the minimal element? Some operation which returns you some statistics but do not change the current state. So you may want to have something like this. So there are some versions, and you only want to modify the last version. So there are version 1, 2, 3, 4. You can access any previous version and find some statistics about this. But you only modify the last version of the data structure. That's the idea. So let's call it the partially persistent data structure. Okay. In partially persistent structure, it's okay to use amortized structure. You will never have situations like this. So you don't have problems when you have some long operations. What else? Yeah, but for Q it's not very interesting, because in Q both operations like add element, remove element changes the state. So for Q it's not interesting. Let's talk about linked lists. So let's have a partially persistent linked list in which you can add elements, remove elements, and iterate over all elements. So let's have it here. So I want to now I will build a linked list, a partially persistent linked list with, like, let's say 3 operations. We will add element, let's say add after again, after. We will, let's suppose, remove element, and let's say we have iterate over all elements. The iterate will just iterate all elements of the list, something like that. You may have more complicated ways, like you want to be able to go in both directions of this list. So you may want to have from left border to the middle and go back, something like that. So you want to be able to walk along this list in both directions. Fine. So how to create a partially persistent linked list? Let's write it right here. There is everything. So, what is the idea? First, let's enumerate all the versions. So every version has some number assigned to this version. So, since the structure is partially persistent, we have some linear ordering on the versions. So we have some old versions and we have some new versions. In fully persistent structure, it's not true, because if you have like this version and these two versions, so which one of them is older, which one of them is newer? So there is no connection between these two versions. But if you have partially persistent structure, you always can compare two versions. So this version is older than this version, and so on. Let's use this and enumerate all versions of the structure from left to right. Cool. Now, how to add new elements in the middle of the linked list? Well, let's have some elements. Let's have some element x. Let's have this element z, and we want to add new element y between that. So you have something here, and so on. So you have this part of the linked list, and you want to add new element y here. You want to add it between element x and z. And let's say now we have versions. Let's say we have version 5. So we have some previous versions. And our current situation is like this. So we have like previous versions, and now we have version 5. So this is the version 5. And after we add element y, we will have version 6. Y, not 5. Element y, we have version 6. And we want to be able to access these both versions. So we want to be able to move along this list and to move along this list, which includes this element y. How can we do it? Let's maintain two versions of these two nodes. So for these two nodes x and z, we will maintain two versions of this node. One version is before we add element y, and another version which uses this node y, like this. And the same for this node z. We'll have another version of this node which knows about this node y. And the idea is like this. When we are in version 5, we use these pointers to go in this version 5 list. And then when we have version 6, we use these pointers. So we have this list which includes element y. But how can we check what version of element x is to use when we walk along this list? It's very simple. We use by the index of the version. We know that this new version is valid when version is from 6. So if current version is greater or equal to 6, then we use this new version of node x. And if version is less than 6, then we use this previous version. So we maintain two versions and this number. This number is saying that if the current version is greater or equal to 6, then please use this version of node x. And before version 6, please use this version of node x. And same thing here. So this new version is used only after 6 version. That's all. That's all. So how do you use this linked list? You have like global variable, which is current version, and like current node. And when you need to move to the next element, you check the current node. It has two versions. Which version can you use, this or this? So you check what is the current version and select one of these two versions of the node, and then use this pointer to go to the next node, and so on. That's how to use. How is x connected to previous element? Just by the same pointers. Yes. Okay, let's talk about this later. Yes, this picture looks cool, but it's not well describe what's really happening here. So in pointer machine model, you don't have something like nested nodes or something like this. Yeah. So this is like a scheme. So what's really happening here? You may have two versions. One version is there are two different techniques how to apply this in real pointer machine model. First way is to just have this big node x, which have two set of fields. Like you have these fields, like previous one, next one, and some data one. We also have some data, right? So we have these fields for the first version of node x, and another set of the same fields for the second version of this node. And you also know this version, yes? So you may want to you may just create from each these element, something like that. So you create this like a big node with two sets of fields and another field which says this version. So yeah, that's perfectly legal, I think. So you just extend your node twice, so it's still constant size node. Another way to do it is like to create like really two versions of this node x. This is the x prime, this will be x, and like another small node, like helper node, which have simply version and two pointers to here and to here. So here you start from this helper node, check what version you need, and then go to either of these versions of the x. So this block just can be implemented like this or like this. Not a big deal. What is the crucial part is that we will never have more than two versions in this block. So in each block like this, we will only have maximal two versions. We will never have more than two versions in the single block. So you can implement it like this or like this. That's important. Now, what happened? This is a simple situation. We add element here, but you have many operations. So at some point you may want to add another element here. So you will try to add another version of block of element z, and you already have two versions here. So there is no room for the third version. What happened? Let's write it here. Let's write it in just to raise this. So what may happen again? You try to add another node z, another node y here. You want to add it between nodes x and z. And nodes x and z already have some previous versions. So there are two versions of node x, something like that, and there are like two versions of node z, and two versions of this node, and two versions of this node, and so on. This may happen. What can you do in this situation? Again, you want to be able to move along this list using these pointers, and also use some another pointers to walk this and go from x to the y and here. And there is no room for any extra pointers here. So what we'll do, we will create another node. So we will simply copy this node x to another node. Let's just have another node here. And move these pointers to this node. And the same for the node z. Just create another node z and make the pointers to this node. Now we need to create pointer from here to node x. But there may be already two versions here. So if there are two versions in this node, then again we copy this node and create it like this. And we do it to the left until we reach node which have no second version. So we go to the left until we find some node which have only one version. And when we find this node, we add second version to this node. So we take this node, add the second version to this node, and do something like that. And so on. And the same thing on the right. So we look on this node. It has two versions. It's called fat nodes. We have fat node here. So we just copy this node to the new node, go to the next one. If it is fat, we just copy it to the new node here, and go to the next. And when we reach first not fat node, we add second version to this node and make pointers here. That's all. If all nodes to the tail have two versions, then we'll copy all the nodes. Yes. It may happen that we reach the end of the linked list and just copy all the nodes. It's fine. Then we just copy all the nodes till the end of the list. Yes, the idea is that never have more than two versions in each node. So each node have at most two versions. Yeah. Now let's calculate the time complexity. What is time complexity? No, worst case time complexity is obviously linear. So in worst case, we may add new element. All elements of the list have two versions. So we start from here and need to copy all elements to the next element, to these copies. This may happen. But let's calculate the amortized cost of this operation. I claim that amortized cost of operation add is constant. Why is this true? No, because it's partially correct, because it's partially persistent. So we only modify the last version of the data structure. So let's have some potential function. Let's say that, again, how to find the good potential function. To find the good potential function, we need to look on the long operation. What happens when we have a long operation? When we have long operation, we copy all these nodes to these new versions. Yeah? So we just go to the closest node fed node and then copy all these nodes to these new versions. And now when we find how the long operation works, we need to find the potential function which is decreasing when we make this long operation. So we start from here and try to find the function which is decreasing when we move from this state to this state. No, and now it's quite obvious. So we want to find something which is decreasing, and what is decreasing is the number of fed nodes. So we will say that potential is simply the number of fed nodes. So when you copy these elements here, so if you copy, let's say, so if you copy k elements here, then you spend the k operations to copy these nodes here, and the change of the potential will be minus k plus 2. So we have these two new fed nodes plus 2. So the amortized time complexity will be 2. Why cannot we stack on each node? Having two versions for each node. Because why do we have only two versions in each node? If you have more than two versions, if you have the list of versions, if you have list of versions, you want to be able to find the correct version. So how to iterate over this list? So when we iterate over this list, we so imagine you are now in some node x, node x. So imagine you want to iterate over all elements of the list, and you now stay in node x, and node x have many versions. Now you want to go to the next element of the list. So you want to find the next pointer. And to find the next pointer, you need to find the correct version you want to use. So you need to find some way to find the good version in this list of versions. And there is no way you can do it in constant time. What you can do, actually, you can maintain a balanced search tree of these elements. That's true. You can make a binary search tree over these versions and find the correct version in logarithmic time. But this will add a logarithmic factor over all time complexity. So you will be able to maintain this operation iterate not in n time, but n multiplied by a logarithm of number of versions. But if you want this iterate to work in linear time, you need to be able to pick the correct version in constant time. Each time you go to some node, pick the correct version, go to the next node, pick the correct version, go to the next node. And to be able to pick the correct version from this list, you need logarithmic time. That's why we only restricted to have only 2 versions. When you have only 2 versions, then you can pick the correct version in constant time. So total time will be linear still. Okay, hope it's clear enough. That's actually all I tried to discuss today. Maybe we have we need some special stream to discuss some topics which just didn't fit in this course, but it's really fun, for example, to discuss how to make this queue, this non-amortized queue out of 6 stacks. It's a fun data structure, so maybe we'll have some additional streams about this. Not sure about this. Maybe at some point. Okay, I think it's all for today. So thank you for joining today.